Hello everyone, welcome to the Stepper Motor and Drives practical in the Laboratory Practice 5 module of Semester 7. So let's get started with a basic introduction to the theory parts you'll need to follow this practical and to prepare your coursework.
First, let's see what a stepper motor is. It's an electrical machine which rotates in discrete angular steps when a programmed sequence of input electrical pulses is applied. To put it simply, it's an electromechanical device which converts the electrical pulses into discrete mechanical movements. Stepper motors are used to control the angular position of the rotor easily without a closed feedback loop. Now, shall we have a quick look at some of the applications of stepper motors? Okay. So they are used in robot arms, DSLR cameras for focus regulation, video cameras for focus, zoom and tilt functions, printers for printheads, paper feed and scan bar, textile machines, data storage tape drives, automated teller machines or ATMs for bill movement and tray elevators, medical industry for scanners, dispensing pumps, samplers and other machinery, engraving machines for XY table motion, gaming machines such as wheel spinners or card shufflers, spacecrafts and many more. Therefore, you can see that the stepper motors are being used in many different areas for accurate positioning systems. So, why do we use stepper motors? Why not some other kind of motors like servo motors? That is clearly because of the advantages of stepper motors over servo motors. The stepper motors are brushless, therefore there are no frictional losses. There is no arcing, which makes them less risky too. They are rugged and thus have a longer lifespan. Open loop positioning of stepper motors. They move in discrete angular steps. Therefore, the position of the shaft is known at all times without any feedback mechanism. Excellent response in starting, reversing and stopping of stepper motors. They are load independent, which means they maintain their set speed irrespective of the load as long as the load is less than the rated torque. They have a simple design and are less costly. Now, let's have a look at the classification of stepper motors based on their construction. As you can see here, there are three main types of stepper motors as permanent magnet stepper motors, variable reluctance stepper motors, and hybrid stepper motors. Variable reluctance stepper motors are further divided into single stack and multi-stack. Moving on to different types of torques involved in stepper motors, you can see number 1 is detent torque. This is the torque produced when the windings are not energized. And number 2 is holding torque. This is the torque produced when the rated current flows through the winding. Let's get a basic idea about the notation used with the stepper motors. Consider a 6x4 pole 3-phase stepper motor. Here, 6 refers to the number of stator poles, 4 refers to the number of rotor poles, and 3 phases refer to the number of phases to which the stator poles are connected. You can clearly see this in the given figure. The 6 stator poles, the 4 rotor poles, and the 3 phases which are marked in red, yellow, and blue. Basic step angle. This is the angle of rotation of the rotor of a stepper motor when a single pulse is applied to the input of the stator. So, you can easily get an equation for the basic step angle as shown here. According to its definition, the basic step angle is equal to 360 degrees divided by the number of pulses per revolution. Now, let's try to derive an equation for the basic step angle in terms of motor speed n expressed in RPM and pulse frequency f expressed in Hertz. Therefore, the number of revolutions per second is equal to n over 60. The number of pulses per second is f. Therefore, the number of pulses per revolution is 60 into f divided by n. So by definition of basic step angle, we know that it is the angle rotated when one pulse is applied. So we can come up with another equation for the basic step angle as shown here. Basic step angle is equal to 360 degrees divided by the number of pulses per revolution. An expression for the number of pulses per revolution has been found previously, right? So, the basic step angle is equal to 6 into n divided by f, expressed in degrees. Also, the basic step angle can be calculated as shown here too. That is, the basic step angle is equal to 360 degrees divided by the product of number of rotor poles and the number of phases. Let's consider a 6x4 pole 3-phase stepper motor and calculate its basic step angle. Here, the number of rotor poles is 4 and the number of phases is 3. Therefore, the basic step angle is 360 degrees divided by 4 into 3, which is 30 degrees. Now, let's move on to the modes of operation of stepper motors. Basically, there are 3 modes of operation discussed in this practical as number 1, single phase on operation, number 2, 2 phases on operation, and number 3, half step operation. We'll have a quick look at these modes of operation one by one. Single phase on operation. In this mode of operation, only one coil is energized at a time as shown here. This method is used in situations where power saving is a concern. The number of pulses per revolution is 4 and therefore the basic step angle is 90 degrees. 2 phases on operation. This is the most often used mode of operation. Here, the coils are energized in pairs as shown in these figures. The number of pulses per revolution is 4 and therefore the basic step angle is 90 degrees. Half-step operation. This mode of operation is a combination of single phase on and 2 phases on modes of operation as shown here. By using this method, the step size can be reduced by half, thereby doubling the steps per revolution. This doubles the accuracy of the positioning system. Here, the number of pulses per revolution is 8 and therefore the basic step angle is 45 degrees. That's the end of the basic introduction to stepper motor and drives. You'll be learning more about this in Electrical Machines and Drives 3 module of this semester. Now let's have a look at the experimental setup of the stepper motor practical. This is the Mercator Lab system that we're using for this practical. This is the microcomputer board and it's used to control the mode of operation and the direction of rotation of the stepper motor. This is the transistor switching circuit and it's controlled by the microcomputer board. This is the manual switching circuit and it can be used to control the operation of the stepper motor manually. This is the DC power supply and these are the terminals of the 3-phase and the 4-phase stepper motor. These are the stators of the AC motor and the 3-phase stepping motor. These are various types of rotors used in the Mercator Lab system. Let's have a look at these one by one. This is the salient pole steel rotor. This is the short circuit winding rotor. And this is a permanent magnet rotor. This is a solid steel rotor. This is a squirrel cage rotor. This is a salient coiled squirrel cage rotor. And this is a semi-hard steel rotor. This is a tachometer. And this is the oscilloscope. So let's proceed with the practical.
Let's move on to part A of procedure, manual switching circuit operation.
First of all, we have to set the voltage regulator dial to its minimum position and also switch off all the main switches.
So this is how we do the connections. First, connect the DC power supply to the manual switching circuit and then connect S1, S2 and S3 to U2, V2 and W2 respectively. Now, this is how we do the connections as explained previously.
And now we are going to insert the salient pole rotor to our 3-phase stepping motor. And now when we rotate the rotor, we can see that it rotates freely without any restraining torque. Let's turn on the main switch and the DC supply and then energize only one phase using the manual switching circuit. And then we have to turn the dial to adjust the current to 1 ampere. Now let us have a look at the rotation of the rotor. Now when we try to rotate the rotor, you can see that there is a restraining torque for its motion.
Okay, so let's move on to the manual switching sequence for a full rotation of the rotor. You are required to fill this table using ones and zeros to indicate the manual switching sequence observed just now. Please add this to your observation sheet. Now, let's move on to part B of the procedure, transistor switching circuit operation.
First of all, we have to set the voltage regulator dial to its minimum position and also switch off all the main switches.
Now, let's see how the terminals of the 4-phase stepper motor are connected to the transistor switching circuit. First, connect the DC power supply as shown here, and then connect the terminals of the 4-phase stepper motor S4, S5, S6 and S7 to T1, T2, T3 and T4 of the transistor switching circuit respectively. So this is how you do the connections as explained previously. Also, make sure to connect the microprocessor board to the transistor switching circuit using this cable. Let's consider the one-phase on operation. Now, flip down the switch SW6 on the microprocessor board to get the one-phase on operation. Then, turn on the main switch and the DC switch. Then, adjust the DC voltage to 12 volts by turning the voltage regulator dial. Once it reaches 12 volts, the 4-phase stepper motor starts to rotate. The direction of rotation can be changed by flipping the switch SW3 as you can see here. Now, let's measure the speed of the stepper motor using a digital tachometer and record the reading. Now, let's consider the two phases on operation. To obtain this mode of operation, flip down the switch SW5. Let's measure the speed of rotation of the stepper motor and record its value. Now, let's consider the half-step operation. To obtain this mode of operation, flip down the switches SW4 and SW5 on the microprocessor board. Let's measure the speed of rotation of stepper motor and record its value too. Observations from the oscilloscope. Here, we are using an oscilloscope to observe the switching signals. All the 4 channels of the oscilloscope are used in this practical since this involves a 4-phase stepper motor. Let's have a quick look at the oscilloscope plots for each mode of operation. You can calculate the time period between pulses using these plots, and it will be needed for your calculations. This is the oscilloscope plot for one phase on operation. This is the oscilloscope plot for 2 phases on operation. And this is the oscilloscope plot for half-step operation.
Here's a little guidance for you to prepare your coursework on stepper motor and drives. Observation sheet. Please use this format for your observation sheet. For part A, under manual switching circuit, please fill this table to indicate the switching sequence observed in the video. For part B, under transistor switching circuit, please record the speeds of stepper motor for different modes of operation as observed in the video. Calculations. You are required to do these calculations for this coursework. Discussion. You are required to discuss about number 1, the detent and holding torques in different types of stepper motors, and number 2, the modes of operation of stepper motor, and draw the steps for a complete rotation under each of these modes. Okay, so that's it for this practical. Hope you enjoyed learning about stepper motor and drives. Have a great day. Thank you.